Hi! In this video we will talk about how we can show that the limit as n goes to infinity of a sum from 1 to n of 1 over k is infinity. And it turns out that there is more than one way to prove this fact, and we will show one way that has to do with a comparison with an integral. And that's a very let's say that's a very standard approach. And then the second way we will cover also uses a comparison approach, but we will use a comparison with a series. So that's what we plan to cover in this video, and we will start with the first approach. Comparison with an integral. So here we have a sum from k equals 1 to k equals n of 1 over k, and that sum can be matched with the sum of areas of rectangles in the following way. The sum from 1 to n of 1 over k is the same as the sum of areas of rectangles that have width 1 and height 1 over k. And this is a Riemann series. Oops, we have n here. The Riemann sum. We have and we are taking rectangles of width 1 and height given by the function evaluated at a point, and let's take the point k, where f is a function 1 over x. So graphically, we have this function 1 over x, and we are evaluating it at 1, at 2, at 3, at 4, and so on. And we're taking rectangles of width 1 and height given by f of 1. So here we have this rectangle of height 1/2. So here is this rectangle. Height 1/3. So here's the rectangle. And we're adding areas of those rectangles up from 1 to n. And then as n grows large, we're adding more and more areas. Then we can say that the sum of the areas will be greater than, well, you can see that the rectangles are actually exceeding the area under the graph of the function. So as we add more and more rectangles, we will have that the sum from k equals 1 to n of 1 over k will be greater than the integral from 1 to infinity of 1 over x. Because the area under the curve for x between 1 and infinity is a proper integral, integral from 1 to infinity of 1 over x. And those rectangles are larger, or going beyond what's under the curve. And this integral can be found by using limits and by using the antiderivative of 1 over x. This integral corresponds to the limit as r goes to infinity of the integral from 1 to r of 1 over x dx. That's the limit as r goes to infinity of the ln of the absolute value of x for x between for x taking the value 1 and r. And that limit is the limit as r goes to infinity of the ln of r without the absolute value, because r is positive, minus the ln of 1, and the ln of 1 is 0, and that limit is infinity. So here we have a limit that is larger than something that diverges to infinity, then we must have that the limit of the original quantity is infinity. Okay, so that's one way we match the series with the Riemann sum. Let's explore a second approach. So I'm going to erase here, and I will start with the second approach. Okay. So a second approach consists of using comparison, but with a divergent series. A series that doesn't converge, a series that is actually going to diverge to infinity. So let's see. So as we take the limit as n goes to infinity of the sum from k equals 1 to n of 1 over k, we're doing 1 plus 1/2 plus 1/3 plus 1/4, 1/5, 1/6, 1/7, and so on and so forth. And I'm going to write some more terms because I will show you how the approach will work very explicitly. So 1 over 13, and let me add some more terms. There you go. So we have 1 over 14, 1 over 15, 1 over 16, and we keep going. Okay. Now, what we would do next is we would start gathering terms in a smart way to generate a series we will know diverges. So how do we do that? So notice that this is this 1/3 is the number 1/3 is greater than 1/4 because 4 is greater than 3. So when we divide 1 by 3, we get something larger than when we divide 1 by 4. So here we have that the series we're exploring, we're studying, is greater than the series with the 1/3 replaced by 1/4. And when we do 1/4 plus 1/4, we get 1/2. And 1/5, 1/6, 1/7 are numbers that are all larger than 1/8, because 8 is greater than 5, greater than 6, and greater than 7. So we can replace 1/5 by 1/8 and say that the sum we have is greater than the sum with 1/8 instead of 1/5, with 1/8 instead of 1/6, and with 1/8 instead of 1/7. And what's nice about this is that when we add those 1/8, we find that we get 4 times 1/8. And that's 1/2. And similarly, we can continue with 1/10, 1/11, 1/12, and so on up to 1/15. And we can say that the sum we're studying is going to be larger than the sum with 1/16 instead of 1/10 instead of 1/11, and so on. And we have 8 fractions that are all equal to 1/16. And if we continue like this, we will find that every time we replace a number 1 over k by 1 over 2 to some power, and that power will be the one that is like the largest, the smallest power of 2 that is greater than k, then we will get a number of addends that would be a power of 2. Here we had 2 addends, and I'll probably just keep it like 2 times 1/4. And then we have 4 addends, and then we have 8 addends, and we will have a power of 2 addends times a fraction, the fraction by which we replaced all those terms of the form 1 over k, where k was not a power of 2. And that fraction will always be of the form 1 over a power of 2, one that goes beyond the number of addends. So we will end up with 1/2. So let me just write this part over here, because that's something we can prove. And then we continue like that. So we end up adding 1/2 by collecting terms in this way. And then when we check the series 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 and so on, we find that this series doesn't converge because you're adding 1/2 at a time, and you're doing that infinitely many times. So that's going to go to infinity. And once again, since we started with a series that is larger than the series that diverges to infinity, we must have that the original series diverges to infinity. So this is another way of proving that the limit we were given is infinity. This limit has a name. The series 1 plus 1/2 plus 1/3 plus and so on is called the harmonic series. And yeah, so here we have 2 ways of proving that that series diverges to infinity. Okay, so now I want to say that if we were interested in showing more details about this step, like have a more rigorous argument here when we go from here to there, then we can use something like we will have to be even more careful. We will have to show more details, but that's something that can be done very easily once we realize that the number of addends will be 2 to the n, because the difference between 2n plus 1 and 2n is 2 to the n. And once we realize that we're replacing numbers by a power of 2, that corresponds to 1 over 2 to the n plus 1. So that's something that can be showed in detail and rigorously, but and if you're interested in that, I can certainly make a video of that detail, those details. So just let me know, and we'll work on that. Okay, so that's it for this video. If you have questions, or if you have more ideas on how to show that the harmonic series diverges, then please make a comment and contact me, and I'll be there. I'll be interested in learning more ways. The second way I showed you is a more recent one, the one I learned about recently by talking to people. I never heard of it. It totally makes sense, but I had never heard of it, so I'm pretty sure there must be many other ways. So yeah, that would be interesting. Okay, that's it for this video. Yes, that will be it. Bye bye.